Hello, welcome to our fourth lecture of linear algebra. Today we are going to be working on some exercises about lines and planes in R3, and this here is our first exercise. So it's pretty simple exercise, which says that we need to find all vectors in R3 that are orthogonal to this given vector. The vector whose components are 1, -2, and 5. So before solving this exercise, let's think a little bit about what this exercise is asking us to do. Okay, so we have a given vector, let's say that this is the given vector, and we need to find all vectors that are orthogonal to this one. Well, if that vector is not a vector 0, which we know that is orthogonal to any other vector, including itself, it's orthogonal to all vectors, including itself. But if it's not the vector 0, the vectors that we are looking for, so we know that 0 is if one of the solutions to this problem, is one of the vectors that we are looking for. If it's not the vector 0, that vector is perpendicular to the given one, so it's forming an angle of 90 degrees with the given one. So if this is a solution, and we change the magnitude of this vector, the resulting vector is going to be also a solution. How do we change the magnitude of this vector? Well, multiplying that vector by a scalar. So this vector is going to be, if that scalar is positive, it's going to be generating a ray here. If that scalar is negative, we are going to be able to go in the opposite direction. So this solution, if this solution, the whole line that vector generates, so the line passing across the origin and parallel to this vector, or containing, in that case, this vector, is going to be also, all vectors in the line are a solution to this problem. But if we also rotate this vector a bit, so now changing the direction of that vector, as long as we keep an angle of 90 degrees here, the resulting vector is going to be also a solution, and we can proceed the same way to conclude that the line that this other vector generates is going to be also a solution to this problem. But I can use any angle to rotate. So if I have this line and I rotate it a little bit, and I get another line, another line, another line, all those infinite lines that I'm obtaining are gonna cover a whole plane. So it seems to be, according to this analysis, that the solution to this problem, all vectors in R3 that are orthogonal to this one, are forming a plane. Is that okay? Oh, so this is a pretty good starting point. And what we are going to do now is use our algebraic tools to solve this problem, let's say, in a little bit more detailed way. Okay? So all vectors in R3 orthogonal to this one. What we know about a vector in R3? What we know about a vector in R3 is that that vector consists of 3 components. So let's say I don't know those vectors, but I know that these vectors have 3 components. Since I don't know them, I will use X, Y, and Z to denote those components, okay? And what I know is that any of these vectors that I'm looking for is orthogonal, okay? I write it this way, is orthogonal to 1, -2, 5. And at this point, we know that this condition here is equivalent to dot product of the vector x, y, z, and the vector 1, -2, 5 must be 0. So this becomes x minus 2y plus 5z equal to 0. But if we look at this equation here, we know that this here is the normal equation of a plane. It's the normal equation of a plane. Oh, so this is matching the result of our previous analysis. So it seems to be that every vector that is orthogonal to this one needs to satisfy this equation, but any vector satisfying this equation is on the plane. On the plane whose normal vector is exactly the given one. Okay? Oh, let's say that this equation is a normal equation, but I don't know. So this is pretty difficult because let's say that I want 5 vectors satisfying this or 10 vectors satisfying this. Well, something that you can do, you say, I don't know how to use this equation for that. Because to me, this equation is a little bit more convenient for if you give me a vector, using it to verify if that vector is on that plane or not. But to generate vectors here, well, maybe I don't know how to do. Well, we have other equations that maybe for you is a little bit more intuitive if you want to generate vectors. Obviously, you can do something like this. Well, let me solve this equation for one of the variables. Heads. To obtain basically the same equation but written a different way. So, okay? Well, not the same equation, but the only thing that we did was a little, a very simple modification. Okay, everything that is here, except for x, went to the other side with the opposite sign. Is that okay? And now if you look at this, that is basically this one, what this is telling us is that I can put any value here in y, I can put any value here in z, and I use this equation to get the corresponding value of x. And now maybe it's a little bit easier for you to see how you can use that equation to generate vectors, because this is telling us, oh, the second component of my vector can be any real number. The third component of my vectors, I can put there any real number as well. I just need to be careful to put a number here that satisfies this formula. So to put a number here that is twice the number that I have put here minus 5 times the number that I have put here. Okay, so all vectors that are orthogonal to this one, which lie on this plane, can be generated using this formula here, where y and z are real numbers. And you can say now, well, but what kind of equation is this? Is this the normal equation? What is this? Oh, this one here is not exactly a normal equation now. This one here is the other equation that we have studied. That is the parametric equation, which I can write it this way. Oh, let's say that I come here and say, y, you're going to be equal to the parameter alpha. Z, you're going to be equal to the parameter beta. And now this equation is telling me that x is equal to 2 alpha minus 5 beta. And if I write it this way, maybe say, oh, right, this is the parametric equation where now alpha and beta are any real number. Oh, but what is the point? Well, what is the point? Well, I can rewrite this equation. I can write this as 0 plus 2 alpha minus 5 beta. Y equals 0 plus 1 alpha plus 0 beta. And z equals 0 plus 0 times alpha plus 1 beta. And now it's obvious that this is the plane passing across the origin, passing across the point 0, 0, 0, and parallel to the vector 2, 1, 0, and to the vector minus 5, 0, 1. Is that okay? So basically what we have is the following. If this is x, this is y, and this is z, I'm gonna represent here my given vector. So I have 1 for x, negative 2, negative 2 for y, and 1, 2, 3, 4, 5 for z. So my vector here This is my given vector. What is my point? 0, 0, 0. So this is my point. And I have a plane passing across this point and orthogonal to this one. So, okay. I have a plane here passing across this point and orthogonal to this vector. Any vector, if I take any point on this plane, 0 is there and this point is also there. So this vector here, the vector whose ending point is this one, the whole vector is on that plane. That's the reason in this case I'm claiming, so I'm not only claiming that the points are on the plane, the whole vector, since the plane is passing across the origin, is gonna be on that plane as well. Is that okay? So all the vectors that are orthogonal to this one are forming a plane whose normal equation is this one and whose parametric equation is this one. And now we know that the solution to this problem is this plane here, which can be described either way. Is that okay? Well, I can change now this problem a little bit. And instead of giving you one vector, I'm going to give you two vectors that are not parallel to each other. So if we look at these two given vectors, they are not going to be parallel. Okay? So to the vectors now, well, let me say that is 3, minus 1, 2, and negative 1, 4, 6. Any two vectors. The main condition here is that these two vectors are not parallel, because if I give you two parallel vectors, basically I'm giving you one. Both vectors are pointing the same way. So it's basically one of the two vectors is completely redundant. Okay? So how can we solve this problem? Oh, pretty similarly. So just to make emphasis, because maybe at this point it's worthy to make some emphasis here. So we are not looking for vectors that are either orthogonal to this one or to this one. We want vectors that are simultaneously orthogonal to these two vectors. Okay, so I'm going to write that. Write that here, just to make it clear. All right? So, but if I look at this single vector, I'm going to represent it here arbitrarily. We know that all vectors that are orthogonal just to this one form a plane. Let me put that plane here, let me call it pi. It's okay? So since the vectors that we are looking for in particular are orthogonal to this one, the solutions to this problem, all vectors that solve this problem, lie on this plane. But not every vector that lies on this plane is a solution to my problems, because I not only want vectors that are orthogonal to this given vector, but also orthogonal to this second one. But if I take the second one, which I will represent it this way, so I'm not using the specific components of these vectors whatsoever. I'm just passing an intuitive idea. Well, what I know is that there is a plane here that is orthogonal to this one, and every vector here on this second plane, every vector here on this second plane is orthogonal to this second vector. So in particular, the vectors that we are looking for also lie on this second plane, which I will name it rho. Is that okay? But if the vectors that we are looking for lie on pi and also lie on rho, they lie on the intersection of these two planes. And the intersection of these two planes is what? What is going to be the intersection of these two planes? Well, the intersection of these two planes is going to be a line. So in this case, it seems to be according to this geometric analysis that the vectors that we are looking for are forming a plane. I'm forming a line. It's okay? Well, what do we know about those vectors? Let's verify that our intuition, our geometric intuition, is correct. So, vectors in R3 again. What do we know about them? Well, that they consist of three components. So, X, Y, and Z are going to be the components of this vector. And these vectors needs to be, every vector that we are looking for needs to be orthogonal to this one. But also needs to be orthogonal to this one. At the same time, so this is a system. At this condition is equivalent to dot product equals to 0. So the first condition leads us to the equation 3x minus y plus 2z equals to 0. And the second condition leads us to the equation minus x plus 4y plus 6z equals to 0. Is that okay? Well, but this here is the normal equation of a line. This here is the normal equation of the line. So it seems to me that we were correct here. And in this case, the point of this line, that specific point that we use to get the normal equation is the origin, 0, 0, 0, because remember that both vectors start the origin, so both planes are passing across the origin. So if you want, this is giving us some insight. Every normal equation of a line is the intersection. So what we are doing is describing that line as the intersection of two planes. Is that okay? Again, if you look at this equation here, this is the normal equation of the plane pi. And if you look at this equation alone, this is the normal equation of the plane rho. Okay, so when we get the normal equation of a line, what we are doing is describing that line as this system where each equation in this system is the normal equation of a plane. And we are describing the line as the intersection of these two planes. Is it okay? Or again, let's say that I don't like this equation. I don't like this normal equation, this system of equation. I want the parametric equation that seems to be a little bit easier to generate points on this line. Well, if you want that, the only thing that we need to do is to solve this system. So it is not problem. The solution set of this system is not gonna be altered if we flip the equation. So I will write minus x plus 4y plus 6z equals to 0 as the first equation. I will put 3x minus y plus 2z equals to 0. And now I will multiply the first equation by 3. I will multiply the first equation by 3, and I will add the first equation multiplied by 3 to the second equation just to modify this equation, just to get rid of this first term here. And I will obtain the system. So I will keep the first equation, minus x plus 4y plus 6z equals to 0. And now 3 times negative 1 plus 3 is 0x. Okay. 3 times 4 is 12. minus 1, I'm gonna get here 11y. 3 times 6 is 18 plus 2 is gonna be 20z equals to 0. So the second equation now is telling us, for example, that y is equal to minus 20 over 11z. And if we go to the first equation now, we'll solve it for x, and x is equal to 4y plus 6z, but y is minus 20 over 11 times z, so I want to put it here. 4 times minus 20 over 11 z plus 6z, which is giving us x is equal to minus 80. I will have 11 as the common denominator, so plus 66, all these over 11 z, which is equal to minus 14 over 11z. And now, oh, it's pretty obvious what the parametric equation of this line is. So I can write x as 0. Let me start with z. I will put z as alpha, and I can write it here as 0 plus alpha. And x is gonna be minus 14 over 11 alpha, which I can write as 0 minus 14 over 11 alpha, and y is equal to minus 20 over 11 alpha, because z is alpha, which I can write as 0 minus 20 over 11 alpha, where alpha is a real parameter. And now it's obvious that this description that we have obtained here is the parametric equation of this line. Okay? That line is passing across the origin and is parallel to the vector whose components are minus 14 over 11, minus 20 over 11, and 1. Is that okay? And notice the following. The more vectors I use here, it seems to be that the dimension of the linear object that is solution to this problem is getting smaller. Okay? So what happens now if I give you 3 vectors instead of 2? Without any redundancy. So I will put here, let's say, 2, 3, 6. Okay? Since these 3 vectors are not redundant, when we put the third plane here, okay, that third plane is gonna intersect this line, but it's not gonna contain that line. So what do you think that is gonna be the solution of this? What do you think that is gonna be the solution of this? The solution of this is gonna be just the origin, according to our geometric analysis. Yes or no? Well, notice the following. The first problem was just 1 vector. The solution was a plane. Second problem with 2 vectors, the solution was a line, which means that the dimension was decreased by 1. But now if we decrease the dimension of a line by 1, well, we're going to obtain an object of dimension 0. An object of dimension 0 is going to be a point. Specifically, the solution is going to be the origin. The only vector that is going to be orthogonal to these 3 vectors at the same time is going to be the vector 0. Oh, let's verify that. Well, I didn't change the first two vectors. So I can keep these two conditions. I just need to add one more. That corresponds to the third vector. All right? Well, this means that the dot product is 0, which we get 3x minus y plus 2z equals to 0. Dot product here is 0 as well, so we get minus x plus 4y plus 6z equals to 0. And we get here 2x plus 3y plus 6z equals to 0. I can change the order of this equation just because this coefficient is a little bit better to eliminate the first term of the other equation. So I'm going to write minus x plus 4y plus 6z equals to 0. And we'll keep the order of the other. What I know now that if I multiply this first by 3 and add it to a second, I'm going to get this one. So I want to put it here 11y plus 20z equals to 0. So I'm just skipping one step. And I will keep the third equation 2x plus 3y plus 6z equal to 0. Okay? To eliminate this term here, I will multiply the first by 2, and I will add it to the third equation to transform it into something easier. So this is going to be minus 2 plus 2, 0x. So let me keep the first. Let me keep the second. Now I have 0x here. If I multiply by 2, I'm going to get 8 plus 3, or 11y's again. If I multiply by 2, I'm going to get 12 plus 6. It's going to be just 18z equals 0. And now I can use the second equation to eliminate this term here. So, okay, well, in this case, I don't need to multiply by anything. The only thing that I need to do is to subtract the second equation from the third to get a new third equation. Okay, so I keep the first. I keep the second. And when I subtract the second from the third, 11 minus 11, 0y. 18 minus 20 is minus 2z equal to 0. All right? Well, the third equation is giving us z0. But if z0, the second equation now, this term goes away, and we get that 11y is equal to 0. The only possibility that we have is y0. z0, this term goes away. The y0, this term vanishes. And we get minus x equals to 0. And we conclude that x is equal to 0. So now the only solution to this problem is the vector 0, as we had concluded from our geometric analysis. Is that okay? So, okay, notice the following. If we think a little bit, I want to make emphasis on the following idea. So, if I give you one vector here, the dimension of the linear object that is solution to this problem was a plane. Yes or no? Or let's say that that solution can be this. If we get the parametric equation of that plane, we just need two vectors. Yes or no? When I gave you two vectors here, the solution to this problem was a line, so we just need one vector here. Can you see the pattern? If I increase the number of given vectors, the dimension of the linear object that is solution to this problem decreases by the same number that I increased it here. Okay? When I gave you 3 vectors, the dimension was 0. The origin, that is not pointing anywhere. So it's not 0 vector, but to generate this space, I will, it's a convention, I will say that this linear object, which has dimension 0, is generated by the empty set. Okay, so I want to write it this way. Okay, and the pattern that I want to make emphasis on here is the following. If just one vector is given, that vector, as used as a parallel information, generates a line. So when I'm finding everything that is orthogonal to that line, I know that the dimension of the linear object that is orthogonal to a line in R3 is gonna be a plane. And the sum of the dimensions needs to be the dimension of the ambient space, the space in which we are working, which is 3. If I give you 2 vectors that are non-parallel, these 2 vectors generate a plane. Is that okay? Using them as parallel information again. And a plane has dimension 2. So the linear object that is orthogonal to a plane in R3 is going to be a line. So the dimension of that plane plus the dimension of that line again is giving us the dimension of the ambient space. If I give you 3 vectors without any redundant vector is generating the whole R3. It's generating the whole R3. And the whole R3 has dimension 3. So now the linear object that is solution to this problem with 3 vectors has dimension 0. And again, the dimension of the linear object that the given vectors are generating plus the dimension of the linear object that is orthogonal to this one needs to be the dimension of the ambient space. And this is going to be a general rule. We are going to be formalizing this. As I said, these first lectures here, I just want to develop some intuition. I can say that I'm not formal enough. I'm not elaborating the concepts and the ideas very formally here because I want to work on spaces that are not new for you. You have seen before in previous courses, but we are going to formalize everything. So my main objective here is to use something that is not completely new for you to develop some intuition behind the main concepts that we are going to introduce a little bit later in a more formal way. Is that okay? So this is going to be always the case. If you have a linear object, okay, and you get the linear object that is orthogonal to the given one, the dimension of the given one plus the dimension of the orthogonal object, linear object, is going to be the dimension of the ambient space. Is it okay? So let's say now that we are in R50, and I'm giving you one vector, one vector in R50. Well, is this rule is valid also in R50, and when we find all vectors that are orthogonal to the given one, well, I know that this one is going to be generating a line in R50. So the dimension of the linear object consisting of all vectors that are orthogonal to the given one, to this line if you prefer, okay, is going to have, well, the sum of the dimensions needs to be 50. So if this has dimension 1, the dimension of that orthogonal linear object is going to be 49. Is that okay? So that's the main idea. That's what I wanted you to keep in mind. We are gonna go over this again, so no problem. And I just want to put that on your brain. Just okay. Okay. So let me give you another problem now. Let me change the problem a little bit. So let's say that the following problem is gonna be something like I'm gonna give you two lines. Okay. Let's say that these two lines in the space, in the 3D space, and these two lines has an intersection, and that intersection is gonna be just 1 point. Okay, so far, well, we have two lines in R3, and these two lines have an intersection, and that intersection is just 1 point. If this is the case, we can find a plane containing these two lines. Okay? So let's say that I have a first line L1, a second line L2, and a plane containing these two lines, I will call it pi. Now let's say that L1 is described by means of a parametric equation. So let's say that L1 is 1 minus 2t, comma, 3 plus t, minus 5 plus 4t, where t is a real parameter. So usually we use alpha, but well, we can use t, s, whatever we want. Is that okay? I'm writing now the parametric equation this way, but notice that, well, this is just x, this is just y, and this is z. So this is equivalent to x equals to 1 minus 2t, y equals to 3 plus t, z equals to minus 5 plus 4t with t real parameters. Is that okay? Okay. Let's say that L2 is also described by means of a parametric equation. All right. And let's say that the equation for L2 is gonna be minus 3 plus t, okay, 5 plus t, and 3 minus 2t. Okay? Well, let's see that these two lines indeed, the intersection of these two lines is a point. Let's verify that these two specific lines that I'm providing you with indeed are satisfying the conditions of the problem that I gave to you this way, geometrically. Okay, how can we find the intersection of these two lines? Well, I will write the second equation the same way. X is equal to minus 3 plus t, y is equal to 5 plus t, and z is equal to 3 minus 2t, and t is a real parameter as well. So that means that if a point is on the line L1, I'm able to find a value for t such that when I put this value here, here, and here, I'm gonna get the first component of that point, the second component of that point, and the third component of that point. And for the same point, I'm going to find a value for t here that is not necessarily the same value that I found here, such that when I put it here, here, and here, I get these components of the same point. Yes or no? But if x is equal to this and x is equal to this, these two are equal. The only thing that we need to keep in mind is that the value of t here is not necessarily the value of t here. So I want to use the same variable here. Okay? I will come here and we say, oh, t, you are not t anymore. You're going to be s. Just because when I set up my system here, if I use the same variable, what I'm claiming is that the value that I need for t here and here is the same, and that's not the case. We know that. So just for this system that I'm setting up here, to understand that the values can be different, I need to change the name of that value. Okay? But if y is equal to this and y is equal to this is equal to this. So I'm going to get 3 plus t needs to be equal to 5 plus s. And if z is equal to this and z is equal to this, I'm going to get that minus 5 plus 4t is equal to 3 minus 2s. And I got a system of equations now with 3 equations and only 2 variables. Is that okay? Which I can rewrite, for example, this way. Minus 2t minus s equals to, this s came here negative, this one goes to the side, minus 4. I can multiply the whole equation by negative 1 to get it this way. Okay? Here I can write this as t minus s equals to 5 minus 3, which is 2. And the last one I can write as 4t plus 2s equals to 3 plus 5, which is 8. And this is the system, 3 equations and only 2 variables. Is that okay? All right. Oh, I'm gonna organize my system in a different way. I will put this equation on top just because I have this beautiful coefficient 1 here, and I will use it to eliminate those terms containing t on the other equations. Okay, so t minus s equals to, if I multiply this equation by negative 2 and I add it to the first, minus 2 times 1 is negative 2 plus 2, 0, so t goes away. Minus 2 times minus 1 is positive 2 plus 1. I'm going to get 3s here. Minus 2 times 2 is negative 4 plus 4, 0. And now if I multiply this equation, that is my first one over there, by negative 4 and I add it to the third equation, I'm going to get minus 4 times 1, minus 4 plus 4, 0, minus 4 times negative 1, positive 4 plus 2, 6, s, and minus 4 times 2 is negative 8 plus 8 is 0. Look at this. Beautiful, my system now. And if I forget the first equation and I use the second to eliminate s on this one, I will multiply by negative 2. Negative 2 times 3 is negative 6 plus 6, 0. Okay, so my system now, and 0 times negative 2, 0 plus 0, 0. So the third equation becomes 0 equal to 0. Everything satisfies that equation, so I can forget that equation. So t minus s equals 0. S is equal to 0. Because 3s equals 0 is s equal to 0. But if s is 0, okay. Oh, sorry, set 2 here. Set 2 here. If s is equal to 0, then t is 2. This is not my intersection point. The solution to this system here are the values of the parameters that I use here or here. Both have to provide us with the same point. So what you do when you get a solution to this system here is using t here to get your intersection point, or using your s here to get your intersection point. Or if I use t equals 2 here, what we are going to get? X equal, this is minus 2 times 2 minus 4 plus 1 minus 3. T is 2, 3 plus 2 is 5, so y is 5. T is 2, so 4 times 2, 8 minus 5 is 3. That means that this intersection point is minus 3, 5, 3. If I use s equals 0 here, I'm going to get minus 3, 5, 3. So we are good. We are good. The two lines, the two specific lines that I'm giving you here have an intersection, and that intersection consists of exactly 1 point. So we are good. We are good. Whatever I'm putting here is happening here. We are good. Right? What else I said? We said that we have a plane pi containing these two lines. Okay? What I want now? What is the problem? Because so far everything is information. Well, again here t is a real parameter. And what I'm gonna say is, find or describe the plane pi using a parametric equation. So find a parametric equation for the plane pi containing both lines L1 and L2. Is that okay? All right. Well, now you see, what do I need for the parametric equation of a plane? What do you need? You need a point, 1 point, x0, y0, z0, and two vectors, a1, b1, c1, and a2, b2, c2, that are parallel to a plane, and non-parallel. If we look at the two vectors themselves, they are non-parallel. Is that okay? And that parametric equation becomes x equals to x0 plus a1 alpha plus a2 beta, y equals y0 plus b1 alpha plus b2 beta, and z equals z0 plus c1 alpha plus c2 beta, where alpha and beta are real parameters. Is that okay? So if we want the parametric equation of the plane pi, what we need to find are the point at 0, y0, z0, and the vectors a1, b1, c1, and a2, b2, c2. But if the plane contains these two lines, any point on any of these two lines is on the plane as well. And we already have 1 point here, or another point here, 1, 3, minus 5, or put any value for t here, or any value for t here. Any point on any of these two lines is on the plane. So we have some information already. I will put it here, minus 3, 5, 3. That is the same one that I have here, but if you prefer, you can use 1, 3, minus 5, or, as I said, use the parametric equations here to get any point that you prefer. Okay, so we are just missing A1, B1, C1. But if you look at this parametric equation of L1, not only you know that 1, 3 minus 5 is a point on this line, you also know that minus 2, 1, 4 is a vector parallel to L1, because that's the way that we construct the parametric equation of a line. Here we put a point on the line, and here we put a vector, or the components of a vector that is parallel to the line. So we know that minus 2, 1, 4 is parallel to the line L1. Is that okay? But the line L1 is on that plane pi, so this vector in particular is also parallel to the plane pi. And we have the first vector that we need. Okay? The same thing for L2. If we look at the parametric equation of L2, not only we know that minus 3, 5, 3 is a point on this line, we also know that the coefficients for t form a vector that is parallel to L2. So I have here that 1, 1, negative 2 is parallel to L2, but L2 is contained on pi, so that vector is also parallel to pi. And these two vectors are non-parallel, so I have everything that I need. Two vectors that are non-parallel, but each of them is parallel to a plane pi. So I come here and I can put minus 2, 1, 4, and I come here and I put 1, 1, and negative 2, and I have the parametric equation, a parametric equation of pi, that is what we were looking for, and this exercise, this problem is completely solved. Is that okay? Good. Okay, our next exercise is the following. So now we have been provided with two planes. We have two planes here. These two planes are described by means of parametric equations, and we want the normal equation of the line that is parallel to pi, is also parallel to rho, and passes across the point 2, 1, negative 3. So let's have an idea. Let's see what is happening here. So we have a first plane. Here. We have a second plane. Here. And we have a line that is parallel to these two planes. Okay? So I can put it here, for example. Okay, so what we have is something like this. I'm putting it this way. Two planes. I'm putting 90 degrees, the angle between these two planes, but not necessarily has to be 90 degrees. Doesn't matter what is the angle between them. It's not the same plane. And we have a line that is parallel to both of them. Okay? We have a line that is parallel to both of them. Okay, so this is... Well, let's say that one of the planes is the board. I have another plane here. and we have a line that is parallel to both. Okay? That means if I translate that line parallelly until I reach the plane pi, that line is going to fall completely inside that plane. The same if I translate that line. Okay? Parallelly until I reach the second plane, that line is going to fall inside that plane completely. Or maybe the line from the very beginning is inside one of the planes or both of the planes, exactly the intersection of the two planes, but maybe not. Is that okay? So this means that if that line intersects one of these planes, that intersection cannot be one point. That intersection has to be the whole line. Is that okay? All right. Okay. So how can we solve that? Oh, let's see. What is the information that this parametric equation of pi is giving us? From this parametric equation, what I can say? Well, if I take here the independent terms, the terms that are not coefficients of any variable, in this case is 0 and 2. So 1, 0, 2 is a point on pi. The coefficients for t, which is -1, 1, and 3, and the coefficient for s, which are 1, -1, and -2, are vectors parallel to the plane pi. Is that okay? Pretty similar for rho. So 3, 4, 2 is a point on rho. The coefficients for t, which are 0, 0, -1, -1, and the coefficients for s, which are -1, 0, -3, are vectors parallel to rho. Okay? Is what these two equations is the basic information, but just looking at these two equations we can get. Obviously, we can use these two equations to generate more valuable information, but just looking at the equations we can get this. Yes or no? Okay. Okay. And notice the following. What we want a normal equation for that line. We want a normal equation for that line. Let me call that line L. Okay? So since L is parallel to rho, what happens with any vector that is perpendicular to rho? That vector is going to be also perpendicular to a line. And since we want a normal equation for that line, what we need is the following. What we need is the following. Two vectors, P1, Q1, R1, and P2, Q2, R2, such that P1, Q1, R1 is orthogonal, is perpendicular to L. The same for P2, Q2, R2 is also perpendicular to L. We need two vectors that are orthogonal to a line L and one point on that line. X0, Y0, Z0. That's what we need. Okay? Oh, we don't have anything that we need. We need to use this information to get what we need. But look at the following. If this is rho and this vector here is orthogonal to the plane and these two vectors here are parallel to rho, this vector that is orthogonal to the plane needs to be orthogonal to these two vectors at the same time. So we can use these two vectors to find one vector that is orthogonal to these two at the same time. This is a problem that we already solved. Okay? Or something that I want to mention is most likely you know from physics or other math courses that if you have two vectors in R3, the cross product of these two vectors is going to be orthogonal to each of the vectors, each of the given vectors. Is that okay? Oh, you can use, in this case, you can use cross product if you prefer. But the technique that we used before not only works in R3, and not only works if we want one vector. So as we see, it depends on, okay? That technique works always in any dimension for any number of given vectors. Is that okay? What happens if we use the technique that we used before to solve the problem of finding a vector that is orthogonal to this one? Oh, indeed, we didn't find one vector orthogonal to this two. We find all of them. In particular, the cross product needs to be there. Is that okay? So that is what is happening. So in this specific case, if you want to use the cross product, feel completely free to do it. But keep in mind that cross product is very specific for R3, and that in general, we don't have a tool like the cross product that works in any dimension. So the technique that we are going to be using in this course here is the one that we used before. Okay? So again, if we find a vector that is orthogonal to these two, that vector is going to be orthogonal to pi. But if a vector is orthogonal to pi, that vector is going to be orthogonal to L. So P1, Q1, R1 is orthogonal, that is the first vector orthogonal to L that we need, is orthogonal to pi. That's the vector that we are going to look for. And we're going to use these two vectors to find a vector that is orthogonal to the two of them. And that vector is going to be orthogonal to rho. But if it's orthogonal to rho, and rho is parallel to L, that vector is going to be orthogonal to L. So the second vector that went here, we can choose it as a vector that is orthogonal to rho. Okay? And the point is given. So this part, we already have it. But maybe I said before, I don't remember, maybe I said before that we didn't have any of the information that we Yes, we have. We have the point, so sorry for that. So the only thing that we are missing are the two vectors. Well, just this time, for you to believe what I'm claiming, I will solve it. For this case, I will solve it both ways. I will solve it the way that I did before, and I will also find the cross product, and I will prove it that the cross product is one of the solutions that we get when we solve it the way that we did before. Is that okay? And what is the cross product? Well, look at the following. I'm giving you two vectors. And we know that orthogonal to these two vectors, we have a whole line. A whole line. What is the cross product? The cross product is, what happens if now, out of the vectors forming this line, I tell you, no, I don't want all the vectors that are orthogonal to these two vectors. I want all the vectors that are orthogonal to these two given vectors, but have magnitude 1. And now it's different. Now we don't have infinite vectors. Now we don't have a whole line. If we fix the magnitude, if we say magnitude equals 1 or magnitude equals 3, doesn't matter, that means from this origin here to the ending point of the vectors that we are looking for, the distance needs to be 1. That means that I can only move 1 from this point up, or 1 from this point down. And now if we add a condition, about the magnitude, so we say orthogonal to these two vectors, but with magnitude 1, 2, whatever, now we don't have infinite vectors as the solution to this problem. We are going to have just 2 vectors if we fit the magnitude. But if in addition I tell you something about the orientation of these 2 vectors, because of the solutions, because now the 2 vectors, the only difference between these 2 vectors, they have the same magnitude, both are orthogonal to the 2 given vectors, but I say, okay, I want that vector satisfied the right hand rule. Okay, that means that I'm fixing also the direction of that vector. That is what is happening with the cross product. That's the reason the cross product is unique, because it's not only orthogonal to the 2 given vectors. The cross product, we are imposing additional conditions to the cross product. One of the conditions is about the magnitude, and the other condition is about the orientation. And that's the reason the cross product is unique. But if we only leave the problem as give me all vectors that are orthogonal to these 2, we are going to have a whole line. So let me do it the way that I did it before, which I say, all right, x, y, z are my vectors. They have to be orthogonal to the first one. So dot product with this one, which is minus x plus y plus 3z is equal to 0. Dot product with this one, which is x minus y minus 2z must be 0. Give me all those vectors. Well, I have here, well, this is a beautiful system. If I add the first equation to the second, so I'm going to keep the first, and the second becomes 0x plus 0y, just 1z equals 0. If z is 0, we get that minus x plus y is equal to 0, so x is equal to y. That means that all solutions to this problem in this case are x. Let me put it this way. I want to put y equal alpha or t, or whichever parameter you want, and alpha 0, where alpha is any real number. Okay? So I have my first, if I choose, for example, alpha equal 1, I have my first vector here. 1, 1, 0. Okay? I can come here and say 1 and 1, and here 0. Obviously, all this is going to go away. I'm just making emphasis on the process. But let me compute the cross product. Well, if I compute the cross product here, I know that minus 1, 1, 3, cross product 1 minus 1 minus 2 is equal to what? Is equal to, okay, 1 times negative 2 minus 3 times negative 1. This is going to be the first component. I don't have a space, so I'm going to continue below. Minus, the second component is going to be minus. It's going to be minus 1 times minus 2 minus 1 times 3. So it's going to be the second component. And the third component is going to be minus 1 times minus 1 minus 1 times 1. Okay, and now 1 times negative 2 is minus 2, minus 3 times minus 1 is positive 3, so 3 minus 2 is just 1. Now we have here minus 1 times minus 2 is positive 2. 1 times 3 is 3, but I have a minus here, so this is going to be 2 minus 3, which is negative 1. With this minus here is 1. Minus 1 times minus 1 is positive 1. 1 times 1 is 1. 1 minus 1 is 0. So you see, well, the cross product is here. It's exactly the one that I chose. It's exactly the one that we get for the value 1 if we assigned the value 1 to the parameter. So you see, that's it. That's the mystery behind the cross product. When we do it this way, using the criterion that we have for orthogonal vectors, setting up this system, we are not just obtaining one vector that is orthogonal to these two at the same time. At all of them, we know that all of them are forming a line. The cross product is one of those. Okay? Why the cross product is unique? Because in addition to be orthogonal to the two given vectors, the cross product, we are imposing two more conditions. One about the magnitude and one about the direction. Is that okay? That's what makes the dot product unique. And again, we don't have a similar tool to solve problems like this in any dimension. So this is the technique that we are going to use to solve a problem like that one. All right? Okay, well, now the only thing that we need to do is to repeat this process for these two vectors. Feel free in this case to use the cross product again, and that's going to be your P2, Q2, R2, and you're going to get the normal equation of the line L. That is what this exercise is requesting from us. Is that okay? I'm going to leave that part to you as an exercise, or just for you to do it. And I'm going to finish today talking a little bit about the meaning of the variables in the equations. Okay? So what happens, for example, if I gave you, what happens if I gave you a plane described by a normal equation, and the variable x does not appear on that equation. Okay? So let's say that I give you something like this. Oh, y plus 4z equals 3. So that means that the coefficient of x is 0. That's the reason why x is not appearing in that equation. What is the meaning of that? What is the geometrical meaning of that? Well, first, this is telling us, if you look at this equation, what this equation is doing is imposing conditions on the components of the points, okay? The conditions that the components of the points need to satisfy for that point to be on the plane. Is that okay? If x is not appearing, that doesn't mean that every point on this plane x is 0. No, it's completely the opposite. If this is the restrictions that we are imposing to the components of that point, if x is not there, what that means is that we don't have any restriction on x. If we don't have any restriction of x, it's not that x is forced to be 0. It's the opposite. X is completely free. We don't care about the value that we are assigning to x. So x can take any value regardless what is the value for y and z. The only ones that are related here, the only one that needs to look to the value of the other are y and z. X can do whatever she wants. Is that okay? That's the first thing. It's a common mistake in many cases when you have an equation of, let's say, a plane, a line, whatever, and you don't have variables there. A variable is not appearing in that system. there is a common mistake to assume that the value of that variable is 0. No, the coefficient for that variable is 0, but the value of that variable is completely free, is whatever. Okay? Okay, I don't have x. But if I look at the equation of this plane, which I can rewrite this way. Look at the normal equation of a plane. How we write it? P times x minus z0 plus q times y minus y0 plus r times z minus z0 equal to 0. But I can distribute here, I can distribute here, and I can distribute here, and this becomes px plus qy plus rz, and then I have this constant minus p at 0 minus qy0 minus rz0 equal to 0. So this is the number d. In my case, well, since I'm writing on this side, it's going to be minus 3. Okay? But look at the coefficients of x, q, and z. The coefficients of x, y, and z. The coefficients of x, y, and z are exactly the components of my normal vector. Is that okay? So when you have the normal equation of a plane, something that you can immediately say is that 0, coefficient of x, 1, coefficient of y, 4 is a normal vector for that plane. Is that okay? But if what I have now is this. This is my plane, and I have a normal vector. All right? But look at this 0. This 0 is telling us something. What happens if I take the dot product of this vector, dot product, with this 1? And why this 1? Oh, because this is a very important vector for us in R3. Because when we have this axis here, we know that the vector 1, 0, 0 is generating the x-axis. So is the vector I, maybe, that you have used in other courses. Is that okay? So this vector is basically the direction of the x-axis. It's the one generating the x-axis. So when I do this, I'm getting information about the position of this plane with respect to the x-axis. But what is this dot product? This dot product is 0. Because it's 0 times 1 plus 1 times 0 plus 4 times 0. Yes or no? But if this dot product is 0, this is telling me that these two vectors are orthogonal. But if this vector is normal to a plane and this vector is parallel to the x-axis, what I have is the x-axis somewhere here. This means that the vector that is orthogonal to the plane is also orthogonal to the x-axis. So the plane and the x-axis are parallel. Okay? So my plane is not crossing the x-axis. My plane at most is containing the x-axis, but not crossing the x-axis. Is that okay? And this is what we can conclude. When we don't have a variable on the normal equation of a plane, what we can conclude is that that plane is parallel to the axis that corresponds to the variable. If it's x, to the x-axis. If the variable that is not there is y, then the plane is parallel to the y-axis. Well, so, is that okay? So you see? All right. But what happens if I give you this? So not only the coefficient for x is 0, the coefficient for y is also 0. So not only x is not appearing there, y is not appearing in my equation either. Oh, what I need to do is to put the two pieces together. If x is not appearing, my plane is parallel to the x-axis. If y is not appearing, my plane is also parallel to the y-axis. But if I look I look at the x-axis and the y-axis together, these two vectors, 1, 0, 0 and 0, 1, 0, are generating the coordinate plane xy. And if my plane is parallel to x and parallel to y, my plane is parallel not only to these two axes independently, it's gonna be also parallel to the coordinate plane xy. Is that okay? You see? So every coefficient here, everything here is giving us some information. And that's what I want. I don't want, I'm not looking for developing in you skills, mechanical skills, you know, how to solve some problems just algebraically, but also to interpret every symbol that we are writing here, interpret everything that we are doing here. Let's go, or at least as much as we can. All right? But what happens now? If this same plane, let me come back to this one, the one in which x is not appearing. We already know that it's going to be parallel to the x-axis. It's going to be parallel to the x-axis. Is that okay? Okay. What happens if we describe that plane using a parametric equation? What happens if we describe that plane using a parametric equation? Well, the only thing that we can say is that 1, 0, 0, or any vector that is parallel to this one is one of the vectors that we are using here. For example, A1 is equal to 1, B1 is 0, and C1 is 0. That's what we can say, because for the parametric equation of a plane, the vectors that we use are parallel. What this is telling us is that one of the parallel vectors can be used as the vector whose components are 1, 0, and 0. Okay? But in this case, we can say a little bit more. If we are missing x and we are missing y, now we can say that the second vector can be 0, 1, 0. Yes or no? But there is something common to my two vectors here, that is that the third component of both is 0. So that means that we are not forced to use these two vectors. We can use any two vectors that are parallel to my plane. And what this is telling us is whichever two parallel vectors that we write here are going to have the third component equal to 0. And why? Because now this means that 0, 0, 1 is orthogonal to my plane. So the vectors that are parallel now here, if these two vectors are parallel to the plane and this one is orthogonal to the plane, okay, well, doesn't matter the value here, because these two zeros, I'm gonna vanish them. But this one is taking just the third component. For that dot product to be 0, I cannot have any value here different from 0, because this one times that value is going to be that value, and my dot product is not going to be 0. So for the dot product of this normal vector with this parallel vector to be 0, since I have these two zeros here, I need a 0 here. And the same for the second one. Is that okay? So this is the kind of interpretation that we can give to the 0 components for the normal vectors and the parallel vectors. Is that okay? All right. Well, I'm going to stop by here today. Thank you very much.